Okay, I wanted to talk about null spaces here. Assume that I have an m by n matrix A, the set of all solutions x bar to the matrix equation, or the vector equation if you wish. A x bar equals 0 bar, right? Okay, I claim that's a subspace of Rn, and it's called the right, or just null space of A, written null of A. This is how your book does it. Okay? So let's actually show that. So we're going to consider all solutions to this system, okay? So all vectors x bar that satisfy this condition right here. I claim that's actually a subspace of Rn. Now, because of the dimensions, first of all, that's an m by n matrix, and that means what? If that's a vector, that's got to be an n by 1 vector. That makes it what? A column vector with n components, right? This then would be what? The 0 subscript m here, if I wanted to put that on there. M. Okay, anyways, let's go ahead and show that this actually is a subspace. Okay, I'm going to do it this way. Suppose x and y are elements of null A, and A and B are elements of the real numbers. These are arbitrary, okay? So freely chosen. Then I have the following. A times ax plus by is what? A times ax plus a times by. Okay, you know the distributive property holds for matrix multiplication. Okay, and then scalar multiplication, I can actually bring that scalar that's multiplying on x on the outside and the scalar multiplying on y on the outside here. And I'm going what? A times cap ax plus b times cap ay. And what's ax and ay? Why, those are 0 because they're elements of the null space. So I'm looking at a 0 plus b 0 is what? The 0 vector. Okay? So that means what? Any linear combination of two vectors from the null space, or from the null set, is what? Actually 0 also, showing that this is actually a what? A subspace of Rn. So I say null space, okay? Okay, so I say here, thus, null A is closed under linear combinations and hence is a subspace of Rn. Okay, so null space. We call that the right null space sometimes because what? The multiplication is on the right, the vector is on the right-hand side of this product. Okay? Okay, different ways people will talk about the left null space of A. One way some people might think about it is a set of all vectors in Rm. These would be row vectors, though, such that what? Satisfy x times A is the 0n vector, okay? So this would be, sometimes people will call that the left null space. There you're talking about rows. I guess using my old notation, I would have the bar underneath, wouldn't I? Okay, the bar underneath. Okay, some people go ahead and take actually the transpose of that, though, and go A transpose x equals 0m, with making it a column vector. Okay, but anyways, I'm not going to do too much with the left null space. Let's talk about the basis of null A. Okay, so once again, A is a real matrix m by n with rank R. Then the system Ax equals 0 has n minus r basic solutions. Okay? Remember that? Okay? Providing a basis for null A. Thus, the dimension of the null space A is actually n, okay, the number of columns minus its rank. Now, if you didn't understand this, let's go ahead and take an example, and it's really easy here. Okay, let's take this example. Okay, suppose I've got this matrix A, 1, 0, 3, 2, 1, 1, negative 1, negative 1, 2, reading down. Okay, find a basis for the null space of A. Okay, the easiest way to do this, well, I found the echelon form for A and the reduced echelon form, which I called R for A. This is actually the row reduced echelon form is easier for what we're approaching here. Okay, so I'm going to use RREF here, okay, instead of just E. Okay, now imagine solutions to this system then. Remember all the null space is, right? The null space is solutions to this homogeneous equation, right? It's just solutions to that. Okay, if I write the matrix x1, x2, x3 transpose, okay? All right, so I've got these columns x1, x2, x3, and I'm using what? The row reduced form with the augmented matrix, okay? Okay, so we're setting this up like we did previously in previous chapters. Okay, just imagine solutions to this. Okay, so what is the first equation saying? x1, 1x1, which is really x1 plus 0 x2s plus x3 is 0. That means what? x1 is actually the negative of x3. x2, likewise, in the second row is what? x3. And then, or of course, x3 is x3, right? Okay, so my matrix, or my vector, x is x3 times what? Negative 1, 1, 1. Okay? Notice that these what? Here, these are my pivot columns, x1 and x2. And this what? This is my free parameter column. Okay? All right? My solutions are written in terms of the free parameter x3, right? All right, so the middle equation, for example, is just x2 minus x3 is 0. The bottom equation is telling us 0 is 0. That's not telling us anything, is it? Anyway, so you could think of the null space of A actually just being the span of this vector, right? So x sub 3 is a free parameter, right? It ranges through the entire real numbers here. So we could say the null space is the span of negative 1, 1, 1. So the dimension is what? What's the dimension of the null space here? The dimension of the null space is 1. Okay? The dimension of the null space is sometimes called the nullity of A. All right, I'm not responsible. That's the name. The nullity is the dimension of the null space. Okay, that's all that means. Okay, let's just double check here what we were talking about previously with this theorem, n minus r basic solutions. Okay, what's the rank of this matrix? Well, the rank you can see is 2. The number of columns is 3, all right, for the unknowns. 3 minus 2 is what? 1. And that is going to be indeed the what? Dimension of the null space. Okay? All right? So it's just saying there's going to be n minus r free parameters if the rank is n. Okay, does that make sense? Okay. All right. Here's another restatement here. Let A be an m by n matrix, then the rank of the matrix A plus the dimension of the null space of A is going to be n. Okay? That should make sense because this is what? R, and the dimension here, as we mentioned, is n minus r. Together they add up to the number of columns. Okay? N. Okay? Does that make sense? Okay, I hope you got that, man. Let's talk quickly about something else called the zero null space, or the null space. We will talk about the zero null space, but the zero subspace first. Suppose V is just R to the n, right? The set of real n vectors, all right? That space, that vector space. Then V has a subspace for all n, as a matter of fact, consisting of the zero vector alone, okay? So let Z be what? The zero n vector, whatever n is, okay? It's obviously closed under linear combinations, right? If I take linear combinations of 0, I get vectors that are back in this set, since that set is nothing but the zero vector. The dimension of that vector space, of a vector space, is what? The number of vectors such that every vector in the space has a unique expression as a linear combination of vectors from the, I should really say, from the basis, right? From the basis. All right, does that sound good? Okay. All right. What is the dimension of Z then? Well, I claim the dimension of Z is actually 0. Okay? Notice that, here's the reason why. Notice that any, scalar multiple of the 0 vector is the 0 vector. Okay, that's all I'm saying right here. A times 0 is always 0 for all A. So that the 0 vector doesn't have a unique expression as a linear combinations of vectors from Z. No, it doesn't have I can't express it uniquely as a linear combination of vectors from Z. So the number of vectors in a basis would be actually what? 0. There is no basis for this in that sense, okay? So we could come up here and previously say the dimension of a vector space is the number of non-zero vectors, such that what? Every vector in a space has a unique expression as a linear combination of vectors from some basis. Okay? Alrighty? So, in other words, the zero vector all by itself is a subspace of dimension 0. Okay? So keep that in mind here. Let's talk about the zero null space then. Okay, now it's time for what? Theorem. Suppose I've got a matrix A, which is consists of real entries, m rows and n columns. Then the null set, or the null space of A, is the zero vector if and only if the rank of A is equal to n. Okay, so if the rank of A is n, then the null space is the zero space. Okay, the null space is the zero space. Here's our quick proof here. The dimension of the null space is 0 if and only if, what? First of all, you're dealing with what? A zero space, okay? But the dimension of the null space is always what? N minus R. That's going to be 0 if and only if n and r are equal. So in other words, where the rank is equal to the actual number of columns. Okay? Alrighty, so the zero null space will appear when the rank is equal to the number of columns. Okay? Alrighty, so you'll get that trivial null space, some people would say, in the case where the rank is equal to the number of columns. Okay, I hope you understood that. It's not too difficult. That should help with some of the homework problems.